Okay, a couple examples where we're going to make velocity time graph and position time graphs for specific accelerations. So what we have in this example is it says that the object starts at an initial velocity of 0 and accelerates at 2.0 meters per second squared for 5 seconds. So the velocity time graph is the easier one to start with. I could make a table of values, or I could use the fact that this represents my slope, or rise over run, to do the velocity time graph. It's accelerating in the east direction from rest, so this is going to be in meters per second east, and I need to go to a time of 5 seconds. 1, 2, 3, 4, 5. So every time I step over 1, I'm going to step up 2. So let's make this, let's make it really easy then. That'll be 2, 4, 6, 8, 10. So every time I step over 1, I step up 2. And because it's a uniform acceleration, I know I'm forming a straight line. And there it is. If I want to know the easiest way to get the straight line, I could also use the formula A equals V2 minus V1 over T, and then just substitute everything. 2 meters per second squared east equals V2 minus 0 over 5 seconds. And then if I multiply both sides by 5 seconds, then I'm going to get a V2 value of 10 meters per second east. Using that to create a position time graph, I'm going to start at a position of 0. Now I have a positive acceleration, and I have a starting velocity of 0, which means I can put the vertex of my parabola there. And so what I get is a concave up parabola where it starts at my vertex. So it looks something like that. Now the only thing I think that would help give us a better guideline, let's say that's 1 second, 2, 3, 4, and 5, is if we knew what position it ended at after 5 seconds. There's a trick you can use related to the velocity time graph, specifically that the area under the velocity time graph is equal to the displacement. In this case, we can imagine that triangle that has a base of 5 and a height of 10. And if we are going to use this trick, then we can say that delta D is equal to the base times the height divided by 2, which would be 5 seconds times a height of 10 meters per second divided by 2, which would give us 25 meters. And that would tell us then that this object would go 25 meters in those 5 seconds. And there it is, a displacement time graph and a velocity time graph for that scenario. Let's do another one. Draw a velocity time graph for an object that is traveling at 50 kilometers per hour when it comes to rest with an acceleration of 1.5 meters per second squared. So V1 here is 50 kilometers an hour. We need to be careful not to mix units. 50 kilometers per hour in meters per second is 13.9. It says it's coming to rest, and we have an acceleration of negative 1.5 meters per second squared. 50 kilometers an hour doesn't say a direction, so I'm just going to say in the direction X for positive or forward or something like that. So, I can do this graph here using the slope. If I make each square 2, then I know I'm starting just below 14, and I can imagine trying to go every time I go over going down 1.5, and that'll work. That's what I've been doing. But I'm going to use instead the fact that I know that it's a constant acceleration to come up with the formula that's going to tell me what time that it's going to reach this V2 at. So the formula is A equals V2 minus V1 over time. And I know I got 1.5 equals 0 minus 13.9. That's a negative 1.5 time. Hopefully it's not an issue for grade 11 physics student, but if you have a variable on the bottom, be polite with my units there. Then the way to handle that is to multiply both sides by that variable. Now, mathematicians don't like that. You basically have to say time can equal 0 if you're going to do things like multiplying and dividing by variables. But since we're not interested in time equals 0, that's not a valid solution anyways. It's not a problem for what we're dealing with right here. So then once I get that, I get negative 1.5 meters per second squared. T equals negative 13.9 meters per second. I can divide both sides by negative 1.5 meters per second squared, and I'll be left with my time. In this case, 9.26 seconds. So if I make these divisions, I started to write them in as 1, 2, 3, 4, but I realized that that was going to be a little small. If I make them 2, 4, 6, 8, 10, then sometime right about here, oh, that's actually not very accurate, sometime right about there, I'm going to get to 0 velocity. And since I know it's a straight line, I don't need to go step by step over 1 down 1.5. I can just connect the two dots in a straight line, and that gets me my graph. Times in seconds, and my velocities in meters per second. When I go to do my displacement time graph, or not my displacement, my position time graph, I know I'm going to do it for the same period of time, so I can put those numbers on right away. 6, 8, 10. If I assume I'm going to start from a position 0, again, it's sort of an arbitrary choice because it's all depending, if you go all the way back to that very first lesson, on that reference point that you're using. But if I assume that, what I have here is I have a negative acceleration, which means I have a concave down parabola. And I know at 9.26 seconds, I'm going to hit a velocity of 0, or my vertex. So this part of the parabola has to happen at t equals 9.26. So what I can see here then is that I'm taking this section right here of the parabola, something like this, where I attempt to flatten them out right about there. Now again, just like last time, it would be nice to be able to put a specific displacement value associated with the total trip so that it sort of scales the whole thing. In this case, I'm going to use that same trick that I discussed before, I have not in any video proven this to you or anything like that, but it is true. To be very specific about it, the area between the graph and the axis gives you your displacement, that green area right there. Here, having just calculated the base at 9.26, and knowing the height from the original of 13.9, I can calculate the area of that triangle. Area equals base times height divided by 2 equals 9.26 meters per, that's seconds, times 13.9 meters per second divided by 2 is going to give me 64.4 meters. So wherever we are here, that spot, it represents 64.4 meters. And that just gives some scale to the all the positions in that position time graph. Now I was trying to talk about, just as sort of an aside, I was trying to talk about displacement and velocity time graphs. So if you have some velocity time graph, and I've just dealt with two very simple situations, but let's say you have a slightly more complicated one. Let's say he starts down here and he comes all the way up, and then he flattens out. If you wanted the displacement associated with this graph, what you would have to do is you'd have to consider three separate areas. You always consider the area between the graph and the curve. Sometimes when people are talking about this, myself included, they get a little bit sloppy and they say, they would say that that it's the area under the curve, but it's not quite right. It's the area between the curve and the axis that you would have to get. So in this particular situation, you can imagine trying to get three separate areas. You don't technically have to get three separate areas. If you have if you remember the area for the formula for the area of a trapezoid, you can treat that whole second section as a trapezoid. But the truth is that, first of all, most people wouldn't remember that formula, myself included. But second of all, it's just easier to chunk it up and deal with them individually. So what I would have here is I would have A1 plus A2 plus A3. Now if you're looking at this and you're recognizing that the green section here has negative velocities, so doesn't that mean the object should be going backwards? And the answer is, when you go to put that area into this graph, you're going to have a base times a height divided by 2, and that height is going to be negative, which is going to mean that whole term is going to turn into a negative, which means, yes, it will be going backwards, or it will be going in the negative direction, and it combines with these other ones. When it combines with these other ones, it will cancel out some of that displacement, just like when you go one direction and then turn around and go the other direction. We'll talk about graphs of motion with more complex combinations as are shown in this graph in a future video, but that's all for now.